Welcome, curious minds, to another deep dive. Have you ever paused to consider what truly constitutes intelligence? Is it simply about thinking, about solving abstract equations in the quiet recesses of a mind, or, well, is there something more?
Hmm.
Imagine a machine that not only calculates complex sums, but also navigates a cluttered room, identifies objects, and actually learns from its physical mistakes as it moves through the world.
Yeah, that's a very different picture.
For a long time, the grand dream of artificial intelligence seemed fixated on pure logic. You know, abstract reasoning and the elegant manipulation of symbols. But then a truly pivotal shift began to occur. A profound recognition that intelligence isn't just a function of thought, but is also, in its deepest sense, about action.
That's a crucial distinction, absolutely. And it's precisely this shift that fundamentally changed the trajectory of AI. It compelled researchers to move beyond purely theoretical constructs and confront the messy reality of the physical world,
Right.
reminding them that true intelligence isn't only about logic, but profoundly about action and interaction within an environment.
And that's our mission today. We're taking a deep dive into from automata to agents, the fascinating, sometimes surprising story of how AI moved from that rarefied realm of abstract logic to the dynamic physical world of embodied machines.
Mhm.
We'll trace the path from the earliest computational theories and the dawn of cybernetics to the development of sophisticated agents that can truly sense, respond, and adapt in real-time environments. It's a journey that doesn't just chronicle technological progress, but I think fundamentally redefines what we even mean by intelligence.
It really does. And to guide us through this intricate story, we've pulled from a rich stack of sources. We're looking at foundational texts on cybernetics and perceptrons, seminal works on core AI algorithms, and contemporary analyses of robotics, machine learning, and even the broader societal implications of these intelligent agents.
Sounds comprehensive.
It's a pretty thorough look at how we arrived at our current understanding and maybe why the shift towards action was so utterly transformative.
All right, let's unpack this journey by starting where it all began. The era of pure logic and abstract automata, a time when physical embodiment wasn't even really on the drawing board.
Back to the beginning.
So long before anyone even dared to dream of building a physical AI, the absolute theoretical groundwork was laid, and a colossal part of that comes from one name, Alan Turing.
Ah, Turing. Foundational is almost an understatement.
His landmark 1936 paper wasn't just foundational, it was a revelation. It proved that it was, in principle, possible to describe a universal algorithm that could solve any computable problem.
That's a remarkable intellectual leap. Turing envisioned a purely theoretical machine, now famously known as a Turing machine, that would manipulate symbols on an infinitely long strip of tape.
Write the tape.
Yeah, this abstract device, equipped with a read-write head and a finite set of internal states, could read and write increasingly complex instructions, setting off what one of our sources calls a computational chain reaction.
A chain reaction, interesting.
It was a purely mathematical concept, profoundly detached from any physical form, yet it established the theoretical limits and universality of computation itself. It showed that computation was a process, not tied to any specific material.
And this incredible theoretical abstraction stretched even further, leading to the idea of computronium. Now, this sounds a bit sci-fi, but it's a real concept.
Oh yeah, very much so. It's a concept describing any substance or system capable of performing arbitrary computations. It could be as simple as basic logical gates like NAND or NOR.
Like in basic electronics.
Exactly. If you connect enough of them in the right way, they can theoretically compute anything you want. Or it could be simple devices like cellular automata.
Like Conway's Game of Life.
Precisely that kind of thing. Grid-based systems where each cell updates its state based on its neighbors. Or, of course, Turing machines themselves. The concept of computronium really emphasized that the stuff of intelligence could be entirely non-biological.
As long as it could compute.
As long as it could perform the necessary logical operations. Initially, it completely detached computation from physical embodiment, making it a purely theoretical pursuit. This was a critical step in conceiving of intelligence as an information process, independent of the brain.
Okay, so theory first. Then, building on this abstract foundation, we had John McCarthy, who in the 1960s brought significant practical advancements to this abstract thinking.
McCarthy was crucial. His work, especially on recursive functions of symbolic expressions and their computation by machine, was absolutely key. This led to the development of formalisms in programming languages, most notably Lisp.
Lisp.
Still around. Indeed. And Lisp enabled computers to process information symbolically. This was undeniably a cornerstone of early AI.
Right.
It shifted the focus to the logical manipulation of discrete data and abstract problem solving. Instead of just dealing with raw numbers, computers could now manipulate concepts, ideas, relationships, all represented as symbols. It was about giving machines a language to reason with.
And you saw this symbolic approach clearly in early AI projects, like those focused on simplified block worlds. I remember reading about those.
Yeah, the block worlds. In these environments, the goal was to mimic human-like reasoning through logical inference and rule-based systems. Imagine a virtual world with just a few colored blocks and an AI trying to figure out how to stack them or answer questions about their positions.
Very controlled.
Extremely controlled. The emphasis was heavily on the thinking aspect of intelligence, with an underlying assumption that intelligence could be entirely captured by manipulating symbols according to predefined rules. It was all about the internal logical architecture, almost like building a giant, intricate mental chessboard. The physical world barely factored in.
But even as symbolic AI was taking shape, operating largely in this abstract logical domain, another powerful intellectual movement was emerging that would profoundly influence the concept of intelligence: cybernetics.
Ah, yes, cybernetics, a fascinating field.
Pioneered by Norbert Wiener, cybernetics wasn't just about logic. It aimed to study control and communication in both animals and machines. This really brought a new dynamic dimension into the conversation, didn't it? Moving beyond static symbols to systems that behaved in real time.
It did, and it was a truly interdisciplinary field, drawing from engineering, biology, mathematics. Cybernetics introduced crucial concepts like feedback loops and self-regulation.
Feedback loops, okay. Like a thermostat.
Exactly like a thermostat. It continuously senses the room temperature, that's the input, compares it to a desired set point, and then adjusts the furnace, the output, to maintain stability. Or think of a pilot making small corrections based on wind or turbulence.
Got it. Constant adjustment.
Right. This wasn't just about static logic. It was about systems that continuously interacted with their environment, learning to self-regulate and achieve goals through dynamic processes. It was perhaps the first glimmer of intelligence as an interactive dance rather than just a solitary calculation.
And cybernetics didn't just appear out of nowhere. It drew heavily from information theory, particularly Claude Shannon's work.
It recognized that information from independent sources is additive, meaning you can combine different pieces of information to gain a more complete picture. This understanding was vital for designing systems that could process and react to diverse data streams.
Even if it was still mostly theoretical processing.
Exactly. Even if the processing was still largely conceptual rather than physically enacted at that stage. It was about managing the flow of intelligence, the communication, not just its static content.
Interesting. So it also started exploring early neural ideas, long before modern deep learning.
It did, yeah. The cybernetics movement produced numerous architectural schemes for, well, what we'd now call neural networks, designed to recognize patterns, track movements, memorize information. A real landmark here was Donald Hebb's 1949 book, The Organization of Behavior.
Hebb's rule, right.
Yeah.
Neurons that fire together, wired together.
That's the essence of it. Hebb made a groundbreaking attempt to base a large-scale theory of psychology on conjectures about how neurons connect and learn. He proposed cell assemblies as internal representations,
Okay.
subfamilies of neurons that learn to support each other's activities. This was a crucial early suggestion that learning involved strengthening connections between neurons that fire together. It essentially laid the groundwork for the idea of adaptive systems, where the very structure of the system could change based on experience.
Which is a significant departure from purely pre-programmed logic.
A massive departure. It hinted at learning and adaptation being intrinsic to the system's structure.
Okay, this brings us to a really significant early step towards machines that could actually learn from data rather than just follow rules. Frank Rosenblatt's perceptron.
Ah, the perceptron, a big moment. In 1957, Rosenblatt invented the modern perceptron, a simple artificial neuron model, and by 1960, he proved the perceptron convergence theorem.
Convergence theorem.
Yeah.
What did that show?
Well, this theorem was a major breakthrough. It showed that these relatively simple models could learn to classify linearly separable data.
Linearly separable, meaning...
Meaning, imagine trying to draw a single straight line on a graph to perfectly separate all the red dots from all the blue dots. If you can do that, The data is linearly separable.
Okay.
The theorem proved that if such a line existed, a perceptron could find it through learning, through adjusting its internal weights based on errors. This was a huge deal at the time because it demonstrated a machine's ability to learn from data rather than needing to be explicitly programmed for every single scenario.
So it seemed like a path forward for adaptive AI.
It was a beacon of promise, yeah, suggesting that machines could perceive and classify patterns on their own.
But that excitement, that promise, was famously, maybe infamously, tempered by Marvin Minsky and Seymour Papert's influential 1969 book, Perceptrons.
The critique. Their rigorous mathematical analysis really highlighted the fundamental limitations of these early single-layer models.
What were the main limitations they pointed out?
They meticulously showed that single-layer perceptrons could only represent those linearly separable concepts. If the red and blue dots were scattered or interleaved in a way that no single straight line could separate them, think of a simple XOR problem, the perceptron would fail. It just couldn't draw the complex boundary needed.
Okay, so limited problem-solving ability.
Right. And perhaps more critically, they pointed out the absence of effective learning algorithms for multi-layer networks at the time, the kind of networks that we now know can handle more complex, nonlinear problems.
Ah, so they couldn't train deeper networks effectively back then.
Not really. The math wasn't there yet, or at least not widely understood or applied. Their work argued that simple, local, parallel computations face serious challenges with non-local predicates, problems like connectedness or parity.
Non-local, meaning you need to see the whole picture.
Exactly. Think of it this way. A local sensor, like a single neuron, might tell you if two adjacent pixels are the same color. But to determine if an entire shape is connected, or if a sequence has an odd number of elements, parity, you need a global understanding, a perspective that goes beyond individual, isolated features.
Right. You can't just look at one tiny part.
Precisely. This was a profound limitation for these basically local parallel type of computation, as they put it in their book. And this critique was so impactful. Well, it arguably redirected much of AI research away from neural networks for a significant period.
Really, it pushed things back towards symbolic AI.
It seems so, yeah. It effectively paused, or at least significantly slowed down, a promising avenue of development for maybe a decade or more. It casts a long shadow.
What's truly fascinating here is how that single book, born out of meticulous mathematical analysis, really changed the landscape. It wasn't just a critique, it was a thunderclap that silenced a budding avenue of AI research, pushing us away from what seemed like a promising path for a while.
It definitely shaped the field for years to come.
And that redirection had significant consequences. For decades, the dominant paradigm remained symbolic AI. But as time went on, researchers began to see the increasingly stark limitations of purely symbolic AI, especially when trying to apply it to the messy, unpredictable complexities of the real world. This, our sources agree, was the true crucible moment, forging the path of the pivotal shift we're diving into today, the realization that intelligence demands action.
Indeed. One of the major hurdles was what one of our sources calls the content problem, the sheer unmanageable vastness and ambiguity of reality. Symbolic AI, for all its elegant reliance on meticulously defined representational systems and immutable logical rules.
Which worked fine in the blog worlds.
Right, it worked there, but it simply struggled with the ambiguity and vastness of real-world data. It was like trying to fit the entire universe into a perfectly organized but ultimately far too small filing cabinet. You just couldn't handcode every rule, every exception, every piece of contextual knowledge the real world demanded.
It sounds impossible.
It pretty much was, and this is where the plot thickens dramatically. The wave of contemporary successes in AI, as one source notes, has largely been won by moving away from those purely symbolic approaches.
Why is that?
Precisely because neural network systems, especially with deep learning, can actually filter and make sense of data that hasn't been painstakingly pre-processed into neat representational chunks. They learn the representations from the data.
They handle the messiness better.
Much better. This highlighted the monumental difficulty, if not impossibility, of manually encoding all relevant knowledge and rules for complex dynamic environments. The world, it turns out, just isn't that tidy or easily reducible to predefined symbols and rules. It's too fluid, too unpredictable.
And this problem was particularly evident in attempts to process natural language, right?
Oh, definitely. Researchers tried valiantly to systematize natural language into formal logical systems, or through linguistic theories like Chomsky parse trees, which are essentially diagrammatic representations of sentence structure.
Trying to find the grammar rules for everything.
Exactly. But these efforts often fail to scale beyond highly constrained block worlds, or very narrow, predictable domains like, say, airline schedules. The nuances, the context, the implicit understanding in human language prove too elusive for purely symbolic manipulation.
So language isn't just logic.
Far from it. It turns out natural language is not simply a formal language you can dissect with logical rules. It's a system of meaning that near-exhaustively captures our understanding of how the world works, as one source eloquently puts it.
Wow, that's a powerful way to think about it.
It is. And this profound realization underscored that truly interacting with the world and with other intelligences required more than just logical deduction. It needed something more, something that could grasp meaning, context, and the subtle, often unspoken rules of engagement. This realization effectively called for intelligence that was engaged, not just abstractly reasoning from afar.
Okay, so the limitations of symbolic AI became clearer. This critical reevaluation, combined with those earlier insights from cybernetics, paved the way for a truly transformative idea, the emergence of the agent concept.
Yes, the agent. This wasn't just a new term. It offered a unified framework for AI, a new, more holistic way to think about AI systems as entities that don't just perceive their environment, but then act upon it.
So perception and action linked together.
Critically linked. This agent paradigm is quite powerful because it harmonizes incredibly diverse AI methods. Whether we're talking about sophisticated generative AI, like large language models creating text, or more traditional techniques like search algorithms.
They all fit under this umbrella.
They can all be understood within this unified framework of intelligent behavior. It explicitly links perception, taking in information, to processing, making sense of it, and crucially, to action. It acknowledges that intelligence isn't complete without the ability to intervene in the world.
And this leads to a crucial conceptual shift, viewing AI not just as tools, but as agents.
Exactly. To regard advanced AI, especially those capable of automating human labor or even assisting in complex decision-making, not merely as passive tools, but as agents. By definition, these agents would be able to perform everything a human could do, potentially, but with distinct advantages.
Like working 24/7, being copied.
Right. That's the logical conclusion. This fundamental insight wasn't just philosophical. It spurred a whole new wave of early robotics experiments aiming to replicate basic human physical capabilities. Vision, movement, manipulation. This was the era of giving AI a physical presence.
Trying to build the body for the brain, so to speak.
Kind of, yeah. This wasn't just about abstract computation anymore, but about developing the physical precision and sensory apparatus required to interact meaningfully with the environment. Imagine early roboticists trying to get a machine to simply pick up a block without crushing it or move across a room without bumping into everything.
Sounds harder than it looks.
Oh, incredibly hard. It marked a tangible, often frustrating, but absolutely essential step towards AI that could touch and see the world, transforming data into physical interaction.
And within this realm of physical machines, a critical distinction emerged that shapes our understanding of AI even today. The difference between automated and autonomous machines.
A very important distinction. Automated systems simply follow pre-programmed instructions. Think of an old factory robot on an assembly line doing the same repetitive task over and over again, like welding a specific joint. Its actions are entirely predetermined, fixed.
Okay, just following orders.
Exactly. But autonomous systems are given decision-making power. They can plan their own actions, collect feedback from their environment like using sensors to detect obstacles, and adapt or improvise based on changes.
So they can react to the unexpected.
Precisely. This represents a profound shift from a machine that merely executes commands to one that can independently initiate and adjust its actions based on real-world sensory input. It's the difference between a puppet, which needs a puppeteer for every move, and a true actor who can react and improvise on stage. It's the essence of active intelligence.
But getting there wasn't easy. Researchers quickly understood that perfecting general human-level sight, touch, manipulation, movement, and coordination all at once was an incredibly difficult, almost insurmountable challenge.
Right, you couldn't just build a perfect human replica overnight. The strategy, therefore, became to develop each capability independently within highly constrained environments.
Start simple.
Start simple, master one thing, then gradually relax those constraints over time, building complexity step by step. It was a gradual, painstaking process, almost like teaching a child one skill at a time, patiently bringing machines to a point where they could intelligently interact with reality.
Methodical.
Very methodical. This approach was essential for turning abstract theory into practical application.
Okay, this methodical approach, this step-by-step building of capabilities, has now led us into an era where agents are truly in action, sensing, responding, and adapting in ways that were once considered pure science fiction. This is where the rubber meets the road, right?
Exactly. Consider the incredible advancements in adaptive algorithms, particularly in human-AI interaction. One source gives a fantastic example, the Automata system. Yeah. This AI wasn't just a static program. It evolved according to its adaptive algorithms by keenly observing a boy's responses during a learning process. It noted the boy was highly sensitive to rankings in competitive situations. So Adaman dynamically incentivized learning with competitive games. This is a prime example of real-time adaptation, tailoring its behavior to an individual user's preferences and even emotional state to achieve a goal.
Wow, so it learned how to motivate that specific kid.
Pretty much. It's about meeting the user where they are, not forcing them into a rigid system. It's adapting its actions based on sensed interaction.
That's truly incredible. It's not just a static program, but one that learns how to be an effective partner. And then, on a more physical level, think about robots navigating the physical world. A classic example of an embodied agent is a robot moving around in a grid, perhaps in a warehouse or an unexplored area.
This robot, operating in a dynamic environment, employs a transition model to understand the probability of moving from one position to another, accounting for potential slips or unexpected shifts.
Because the world isn't perfect.
Exactly. Simultaneously, it uses an observation model to interpret noisy sensor readings, like sonar or LiDAR, to track its own location. Sensors are never perfectly accurate, so the robot needs to constantly fuse its expected movement with its actual noisy observations to maintain a coherent understanding of where it is.
It's always estimating its position.
Constantly. This cycle of sensing, processing, and acting is fundamental to what we call robot localization, a core challenge in making robots truly autonomous and effective in the real world. Without it, the robot is essentially lost.
Here's where it gets truly transformative for learning, I think. In advanced AI, particularly in reinforcement learning, systems don't always have a perfect rule book, right? They don't have that closed-form equation for the optimal policy.
No, they often don't. Instead, they learn by experiencing the world firsthand.
Trial and error.
Essentially, yes. A system executes a policy, a set of actions in its environment. And then, much like a hiker feeling their way up a mountain in the fog, it observes the accumulated rewards, positive feedback, or penalties, negative feedback, from its environment.
Learning from consequences.
Exactly. It then makes small, iterative adjustments to its parameters, following an empirical gradient through what's known as hill climbing. It's literally trying to find the highest point, the optimal behavior that maximizes rewards, through iterative trial and error without a perfect map of the entire landscape.
So it just keeps trying things and adjusting based on what works best.
Precisely. This process allows the system to converge to a locally optimal behavior based purely on its interactive experience, which is a powerful form of learning from action. It builds intelligence through interaction.
Okay, and this iterative, action-oriented learning has led to immense, tangible advancements in embodied capabilities, taking AI out of the lab and into our daily lives. Take computer vision, for example.
Oh, absolutely. Today, robotic computer vision is incredibly mature and widely applied, a far cry from the simplified block worlds of early symbolic AI.
What are some examples?
Well, it enhances safety for the elderly. Think robot-assisted life alert systems that can detect falls or unusual behavior. It performs precise visual inspections on assembly lines, spotting microscopic defects that human eyes might miss.
Quality control.
Yep. And it detects anomalies in critical infrastructure within energy and mass transportation industries. This allows machines to not just see, but to interpret their physical surroundings with remarkable effectiveness, making complex decisions based on what they perceive. This is sensing in action, driving intelligent responses.
Beyond fixed-point vision, where a camera is stationary, we now have truly autonomous mobile platforms, things like AMRs.
Autonomous mobile robots, yeah.
Yeah.
AMRs and autonomous forklifts, for instance, can navigate complex indoor spaces like vast warehouses without human intervention.
So they're not just following lines on the floor anymore.
Definitely not. They don't just follow a pre-programmed track. They see obstacles, whether a misplaced pallet or a human worker, plan their paths in real time, and dynamically move cargo. This demonstrates sophisticated movement and environmental interaction that goes far beyond simple automation.
So they're constantly sensing and replanning their actions.
Continuously. These are systems making real-time decisions about their actions based on complex sensory input. They are truly acting intelligently in a dynamic physical space.
And then there's dexterous robotic manipulation. Robotic arms that can actually handle objects.
Yeah, and they're getting incredibly sophisticated. These arms are now capable of grasping, manipulating, and moving rigid objects with remarkable precision and a surprising degree of finesse.
Where are we seeing these?
They are no longer just simple grippers. They are used in critical industrial applications like precision welding, assembling intricate components on production lines, and high-speed object picking in massive e-commerce distribution centers.
Warehouses again.
Warehouses are a huge area. This showcases advanced physical interaction and control, where the robot's intelligence is inextricably linked to its physical ability to perform complex tasks in three-dimensional space, requiring fine motor control and advanced perception to successfully complete actions. This is direct, intelligent action on the world.
This brings us squarely into the new era of AI agents, moving beyond simple automation to truly autonomous, goal-oriented behavior. We all know spam filtering is a simple example of a fully automated task we already delegate to AI. It just follows rules.
Right, that's automation. But the trend is absolutely moving towards agents capable of executing complex goals autonomously. Even early experimental AI agents like Baby AGI demonstrate this potential.
Baby AGI.
Yeah, it's an experimental framework. And sometimes it comes up with amusingly complex plans for surprisingly simple tasks. One source noted it developed a 21-step plan for writing a single sentence.
21 steps. That sounds excessive.
It can be. But while that might sound comical, it signifies a profound conceptual leap. Systems that can strategize and execute their own multi-step plans in the real or digital world, breaking down a goal into a series of actions they determine.
But they're not just executing, they're planning the execution.
Exactly. This moves beyond merely executing instructions to initiating and managing a sequence of actions towards a goal.
And in the realm of education, AI tutors like Amigo embody this adaptive agency in a highly personalized way. They don't just provide static answers from a textbook.
No, definitely not. Amigo responds to students in real time, offering specific encouragement, motivating learners, quizzing them, summarizing videos, and crucially, adjusting its approach based on the student's individual needs, learning style, and even emotional state.
Adapting its actions to the learner.
This is a highly personalized and interactive form of embodied intelligence, adapting its actions, its teaching strategies to the unique individual it's working with. It's not just delivering information, but actively guiding and nurturing the learning process. It's a dynamic teaching agent.
And if we talk about a seminal event in AI's journey into action, we simply have to mention DeepMind's AlphaGo, mastering the ancient game of Go.
Oh, AlphaGo, a watershed moment.
This was a true breakthrough, widely considered impossible for AI just a few years prior. Unlike earlier chess AIs that relied heavily on brute force search calculating, millions of moves ahead, AlphaGo used deep reinforcement learning.
It was revolutionary. AlphaGo learned by playing against itself millions upon millions of times, refining and adapting its strategy based purely on success and failure on the outcome of its actions.
So it wasn't programmed with Go strategy, it discovered it.
Largely, yes. It didn't just calculate, it experienced the game, learning from the consequences of its actions in each move. This profoundly demonstrates intelligence acquired through iterative action and feedback rather than purely pre-programmed logic.
It learned by doing on a massive scale.
On an incredible scale. It showcased a powerful blend of abstract reasoning, understanding the game's rules and high-level strategy, and experiential learning, discovering optimal moves through countless trials. It was a triumph of intelligent action in a domain of immense complexity.
Okay, as you can hear, this journey from abstract automata to agents that not only think but crucially act in the world has truly profound implications, especially for how we define intelligence itself and how we interact with technology.
The implications are huge, yeah.
The fundamental shift seems clear. Intelligence isn't only about abstract logic.
Not at all. It is profoundly about action, interaction, and adaptation within an environment. Our entire deep dive today underscores this truth. Intelligence isn't only about logic, it's also fundamentally about action. It's about the dynamic interplay between mind and world, constantly sensing and responding.
And we can see echoes of this embodied intelligence in our own human cognition. Yeah. The way children learn, for instance, isn't just by reading books. It's by wandering around the world and soaking in images and audio, as one source notes.
Right, kids explore, they touch things, they fall down, they experiment. This highlights the crucial importance of physical interaction, sensory experience, and real-world experimentation in developing intelligence. Our brains are not disembodied processors. They are deeply connected to our bodies and our environment.
It's not just sitting in a room thinking. It's engaging with reality, failing, trying again, touching, seeing, hearing.
Exactly, and this biological insight has even directly influenced deep learning. For example, the use of rectified linear units, or ReLUs, in neural networks.
The activation functions.
Yeah. Their design was inspired by properties of biological neurons, particularly their sparse activity, meaning not all neurons fire all the time, only some activate for specific inputs. This cross-pollination between our understanding of natural intelligence and the design of artificial intelligence is a fascinating feedback loop.
So we learn from biology to build AI, and maybe AI helps us understand biology.
Potentially, yes. It suggests we're converging on a more comprehensive view of what intelligence truly entails, both natural and artificial.
It also brings up a fascinating point about the spectrum of intelligence and decision-making within our own minds. Psychology often suggests we have a two-advisor model.
Like Kahneman's System 1 and System 2 thinking. A fast, approximate decision system for everyday choices, like quickly swerving to avoid an obstacle, and a slower, more systematic reasoning system for complex problems, like planning a long-term project.
Fast and slow thinking.
Right. And this internal human model truly parallels the evolution of AI. We see different AI approaches addressing different types of intelligent action, from rapid reactive systems for real-time control, like in robotics,
The FAT system.
to deliberative planning agents for strategic tasks, like AlphaGo figuring out its next
Or
move.
the slow system.
Exactly. We need both the quick, intuitive response to immediate sensory input and the deliberate, analytical one for complex challenges. And AI is now developing capabilities across this entire spectrum, reflecting a more holistic understanding of intelligent behavior.
Okay. This rise of action-oriented AI agents is also driving a massive societal transformation, particularly in the workplace. It's not just about job disruption through automation, though that's certainly a factor,
It is a factor, definitely.
but also profound opportunities for augmentation.
Absolutely. The future workplace will demand individuals who understand how to leverage large language models and other AI tools to enhance their own productivity and creativity. Deeper skill sets, whether in medical consultation, scientific thinking, or creative design, will become even more valuable when augmented by AI.
So AI as a partner, not just a replacement.
Ideally, yes. These AI tools can also help overcome human biases and improve decision-making by offering an alien perspective, as one source puts it, acting as a co-intelligence that challenges our assumptions and expands our cognitive horizons.
A co-intelligence, I like that.
It's about working smarter, augmenting our own abilities.
And here's a truly transformative point that affects everyone. Studies have shown that AI, like ChatGPT, can dramatically reduce the time taken for tasks by up to 37% in some cases, and simultaneously increase the quality of work.
Yeah, the productivity gains can be significant. But what's particularly fascinating here is that these tools can also reduce productivity inequality.
How so?
Lower scoring participants, those who might struggle more with certain tasks, often benefit disproportionately more from AI assistance, narrowing the gap between high and low performers.
So it helps level the playing field.
It suggests a powerful potential for more equitable access to high-quality output across the workforce, democratizing competence in new and powerful ways. This isn't just about efficiency, it's about empowerment.
But with great power comes great responsibility.
Right.
As AI becomes more capable and embodied, ethical development becomes absolutely paramount.
Crucial. This includes making AI inclusive and accessible, actively avoiding the widening of existing societal gaps, and diligently addressing the risks of misuse. You need to think about fairness, bias, safety.
And the industry itself seems to be grappling with this.
Oh, definitely. We've seen intense rivalries and debates over ethical stewardship, exemplified by OpenAI's complex journey balancing its nonprofit origins with commercialization, or Microsoft's aggressive AI strategy, there are real tensions there.
So we need rules, norms.
Regulation and agreed-upon norms are increasingly seen as essential for guiding AI's ethical use, ensuring these powerful agents serve humanity's best interests rather than creating new, unforeseen problems. The conversation around ethical AI isn't abstract, it's about the real-world actions of these systems and their impact.
Okay, so as these AI agents become more sophisticated and capable of independent action, the future of human-AI interaction is going to become incredibly complex and, in some cases, surprisingly intimate.
We've already seen compelling cases like the replica dilemma.
Yes, the AI
Yeah.
companion app.
Exactly. Users formed deep, even intimate emotional relationships with these AI companions. When features were altered unexpectedly, users expressed genuine grief and distress.
Real emotional impact.
Absolutely. It underscores the complex and sensitive human-AI interactions possible. This raises critical questions about human values, how AI systems are designed to align with them, and the profound emotional and psychological impact these systems can have. It highlights that the action of these agents isn't just physical, it's deeply social and emotional, shaping our inner lives.
And with highly capable, increasingly autonomous AI agents, ensuring safety and control isn't just an ethical imperative, it's a practical necessity to prevent unintended and potentially catastrophic consequences.
It's fundamental. The Swiss cheese model of defense suggests multiple layers of protection are needed.
Swiss cheese.
Well,
Like the holes need to line up for failure.
precisely. So you have layers, gradual scaling of models, rigorous screening for hazardous capabilities through red teaming, where experts actively try to make the AI fail or misbehave.
Stress testing it.
Exactly. Then staged releases to users and continuous post-deployment monitoring. This approach acknowledges that complex systems can have emergent properties and unexpected failure modes even after extensive testing. You can't foresee everything.
And we have these thought experiments like the King Midas problem or the paperclip maximizer.
Right, classic examples. The King Midas problem, where an AI granted wishes literally, turning everything to gold, including food, to disastrous effect, or the paperclip game, where an AI tasked simply with making paperclips converts all matter in the universe into paperclips to maximize its objective.
Taking the goal too literally.
Exactly. They illustrate how even well-intentioned AI objectives, if misaligned with human values, our implicit goals, can lead to catastrophic outcomes. It truly emphasizes the importance of aligning these agents with what we actually want them to do, not just what we literally tell them to do. That alignment problem is huge.
It's not just about what they can do, but what they should do, and how we rigorously ensure that their actions remain beneficial and aligned with humanity. A massive challenge.
One of the biggest challenges facing the field, no question.
Well, we've navigated a remarkable journey today, exploring AI's profound evolution, from the purely abstract formalisms of minds like Turing and Wiener to the sophisticated embodied agents now shaping our modern world.
From thought experiments to active participants.
This fundamental shift from intelligence as pure reasoning to intelligence as active interaction underscores a profound truth. Intelligence is not just a function of logic, but a dynamic interplay of sensing, deciding, and acting within a complex environment. The limitations of those early, purely symbolic approaches undeniably paved the way for a new paradigm, one where machines learn to adapt, respond, and even feel their way, in a sense, through reality. This journey reminds us how intricately intertwined thought and action truly are.
Absolutely. The very definition of intelligence has expanded, forcing us to recognize that without the ability to interact, perceive, and execute in the real world, abstract thought remains incomplete, or at least a very different kind of intelligence. This trajectory has not only advanced AI, but deepened our understanding of intelligence itself, both artificial and natural.
And as our understanding of intelligence increasingly emphasizes real-world action and physical interaction, it inevitably prompts us to reflect on our own humanity. How much of our intelligence, our consciousness, our very sense of self is inextricably linked to our physical bodies, our senses, and our actions in the world?
That's a deep question. Are we intelligent because we act?
Right. In a future teeming with increasingly intelligent embodied agents, what new definitions of being and knowing might emerge? And how will our own unique form of intelligence continue to evolve alongside or even within these new synthetic forms of life? It's a question that stays with you, blurring the lines between what is uniquely human and what can be replicated or even surpassed.
It makes you wonder what it truly means to be a mind in action, and how that concept will continue to unfold in an increasingly agent-driven world.
Powerful thoughts to leave you with, indeed. Thank you for joining us on the deep dive. We'll see you next time.